In 2025, closed-source models like GPT-5 and Gemini DeepThink achieved gold medal performance on prestigious mathematics competitions. But how do we achieve similar results with open approaches? DeepSeekMath-V2 recently scored 118 out of 120 on the Putnam 2024 competition and demonstrated gold-level performance on IMO 2025 and CMO 2024. More importantly, this paper reveals a systematic approach to self-verifiable mathematical reasoning, where AI models learn to identify issues in their own proofs without external validation. Let's examine how this system works and what makes it different from existing approaches. Current AI reasoning models are trained by rewarding them only when their predicted answers match ground truth. While this approach enabled models to excel at quantitative competitions like AMY and HMMT, it has fundamental limitations. The first issue is that correct answers don't guarantee correct reasoning. A student might write random steps like x equals 5, then x equals 4, then x equals 2, and still arrive at the right answer. Final answer rewards would give full credit to this flawed logic. The second issue is that this approach fails for theorem proving. Many mathematical problems require proving statements without numerical answers. The value lies entirely in rigorous step-by-step derivation, not a final number to check. The result? Models that can't distinguish valid proofs from flawed ones. So, how do we verify proof correctness when there's no answer key to compare against? The key observation is that human mathematicians can identify issues in proofs without knowing the solution beforehand, spotting logical gaps, unjustified steps, or flawed reasoning. This suggests AI models can potentially learn similar verification capabilities. DeepSeekMath-V2 trains a separate verifier model using a 3-tier scoring system. A proof receives a score of 1 if it's complete and rigorous, with all logical steps clearly justified. It gets 0.5 if the overall logic is sound, but has minor errors or omitted details. And it receives 0 if there are fundamental flaws, fatal logical errors, or critical gaps. The verifier produces detailed analyses explaining identified issues, and this verification capability becomes the foundation for improving proof generation. When training the verifier model with only score accuracy as reward, a problem emerged. The model could hallucinate fake errors, yet still predict the correct score. For example, it might claim step 3 incorrectly applies the Pythagorean theorem when step 3 never mentions it, but still output 0.5 correctly based on other real issues. Since only the final score matters, these hallucinations go unpenalized, showing that score-only feedback is too coarse. To address this, they introduced a meta-verifier model that evaluates the verifier model's analyses. This second model checks whether the identified issues actually exist in the proof and whether these issues logically justify the assigned score according to the evaluation rubrics. Think of it as verification of verification, ensuring the verifier model's critique is accurate, not fabricated. This improved the verifier model's quality score from 0.85 to 0.96 on the validation set. Importantly, they trained one unified model that can perform both verification and meta-verification tasks, depending on the input prompt. While the verifier model can evaluate proofs externally, the proof generator needs to develop its own self-verification capability. Why? Because iteratively calling an external verifier after each generation attempt is inefficient. Specifically, the approach trains the proof generator model to output both a mathematical proof and a self-analysis following the same format as the verifier model. The reward structure combines two components: 76% from proof quality, as assessed by the verifier model, and 24% from self-evaluation accuracy. This creates specific incentives. If you write a flawed proof and claim it's perfect, you lose points on both components. If you write a flawed proof but honestly identify the issues, you get credit for accurate self-assessment. The highest reward comes from writing correct proofs and accurately recognizing their rigor. The key insight is that the proof generator becomes explicitly aware of its reward function, instead of blind trial and error. When training, the proof model and verifier model create a self-improving cycle. The verifier model improves the proof model through feedback. As the proof model improves, it produces harder proofs that challenge the verifier model's capabilities. These challenging cases become training data to improve the verifier model itself, which then further enhances the proof model. Initially, human experts labeled proof correctness, but as problems became harder, manual annotation became too time-consuming. The automated pipeline generates multiple analyses using the verifier model. When issues are detected, the meta-verifier validates them through multiple checks. If verifications agree on problems, the proof gets that score. This automated pipeline eventually replaced human annotation while maintaining expert-level accuracy. On the hardest competition problems, like IMO level, single-shot generation often produces incomplete or flawed proofs. To address this, the system scales test time compute by generating and verifying multiple proof attempts. The strategy maintains a pool of 64 candidate proofs per problem. For each proof, the verifier model generates verification analyses, and the top-scoring proofs are selected. Each proof is then paired with 8 verification analyses that identify potential issues, and the proof generator refines it based on this feedback. This repeats for up to 16 iterations, or until a proof passes all 64 verification attempts. As a result, successfully solved problems show all verifications passing, a strong confidence signal. For unsolved problems, the model typically identifies genuine issues in its own proofs, demonstrating calibrated self-awareness. On IMO 2025, the International Mathematical Olympiad and the premier global high school mathematics competition, DeepSeekMath-V2, solved 5 out of 6 problems, achieving gold medal level performance. On CMO 2024, the China Mathematical Olympiad, it solved 4 problems completely with partial credit on another, again reaching gold medal level. On Putnam 2024, the premier undergraduate mathematics competition in North America, the system scored 118 out of 120 points. Comparing to formal methods, formal proof systems like AlphaProof and SeedProver achieved similar competition results but require formal mathematical languages. DeepSeekMath-V2 uses natural language reasoning, offering greater accessibility. Traditional approaches assume verification is easy. If you can check answers, you can train models with reinforcement learning. DeepSeekMath-V2 tackles the harder problem, verifying reasoning quality when there's no answer key, evaluating mathematical argumentation itself. This matters because most real-world problems lack answer keys. Scientific research, novel theorem proving, and open mathematical questions require AI systems that evaluate their own reasoning without external validation. Overall, DeepSeekMath-V2 demonstrates a systematic approach to self-verifiable mathematical reasoning, training models to identify issues in their own proofs and iteratively improve without external validation. While closed-source systems reached similar performance earlier this year, this work provides an open methodology for the research community to build upon. Thanks for watching.